Good morning. So this is our 419 computable general equilibrium models. Here in this lecture, we're going to look at very simple models of taxation, and we're going to look at both the numerical solution, how do we solve these things, these models, and then using that solution, we're going to go backwards to calibrate, to see how we calibrate the parameters of the model when we have data. Of course, that data will be simulated data, but we're gonna behave we're gonna behave in such a way that this is the actual data, all right? Because this is just an example. So let me share my screen now. Okay, so this is the handout. You are already given this handout, and here we have two firms, and these two firms will produce two goods using different technologies. One of the firms is using the green technology, and the other firm is using the dirty technology. So here, of course, we are talking about environmental consequences of these technologies. And the government is doing something very simple, basically taxing the firms, okay? And this tax is so the taxation is such that the average cost is increasing for all firms in a percentage manner, right? So if the tax rate is tau, then the firm pays a tau fraction of the total average cost to the government, and then the government rebates all this tax revenue to the household. So there's only one household in this simple model. There could be many. It doesn't really change the environmental part of the model a lot, because people are going to consume that, these goods anyhow. So one person or 1,000 person doesn't really matter for our purposes here. And there's no physical capital as well. All right, the model is very simple. There's just labor. Okay. Now there will be two versions of this model. In one version, we are gonna assume away the negative externality. All right, because environmental problems will have, of course, some negative effects on people's welfare, right? So, but in the first version, we're just gonna assume that households do not realize, households do not really get this utility from environmental problems, okay? So that will be the simplest version, where there is dirty output and green output, but this will not be affecting the utility of the household, okay? In the second version, we're gonna put the externality term in this utility function. So the utility function you see here, okay, basically depends on only consumption, of course, consumption of the green good and the consumption of the dirty good, but there will be an externality term here, and that will be decreasing utility of the household, but that will be in the second part. Okay, so in the first part, the model environment is very simple. We have one household, right? One household. So under section 1.1, we talk about the demographic structure, endowments, and preferences. So there's one household, and this household has a unit of labor. Okay, so that you can imagine that this is time, but it is fixed anyhow. And since the consumer or the household doesn't care about leisure, he or she supplies the entirety of the labor endowment to the market. Okay, so the labor supply will be inelastic, and this is a simple Cobb-Douglas utility function, right? Now let's look at technologies, and in technologies we're gonna assume that there's intermediate input relationships as well. Okay, so we write the technology exactly as in your textbook, right? So this is simply the model in chapter 3 in that regard, but we have only one factor. Okay, so value added for the green technology depends on this production function. So here I have theta g. So this theta g is a productivity parameter, right? And then LG is the labor employed by the green firm, right? So this is positive, and this is a linear production function, okay, for value added. And then a similar production function is there for the value added of the dirty firm, right? So theta D is the productivity parameter, and LD is the labor demand of the dirty firm, right? Now, of course, total output will depend on, will be determined by this Leontief production function. Why? Because there is input-output relationships, right? So when the green firm produces YG, this is tied to value added, and it is also tied to the inputs, intermediate inputs, the green firm uses by itself. So this is the green firm's own output used as intermediate input, YGG, okay? And YDG is the amount of intermediate input used by green firm, and this intermediate input is supplied by the dirty firm, right? And a similar thing is occurring here, of course, depending on the intermediate input, Leontief matrix coefficients, input-output matrix coefficients, right? So these A's, AGG, AGD, ADG, and ADD are the input-output or technical coefficients, and VG and VD are the constants that transform value added to output, okay? So these are, we're going to assume between 0 and 1, as is typical. And taxation, so here we assume that the government taxes both firms, okay? So tau G is the tax rate on the first firm, green firm, and tau D is the tax rate on the cost of the dirty firm, right? Now the tax revenue is given to the household as a lump sum transfer. Since it is lump sum transfer, it doesn't really affect, so it only affects the income, right? Basically. So we introduce the price normalization here in this way. So we normalize the price of the green good to 1. Okay, and then we're going to assume that the green good clears via the Walras law. Okay, this is pretty standard, and you already know what they mean. Now we can look at the households problem. This is a very simple problem right now. It's a simple Cobb-Douglas utility function. There is a budget constraint. A particular share alpha is spent on the green good. The remaining share of the budget is spent on the dirty good. Okay, so these are demand functions. And then we have the firm's problem. Now, in the firm's problem, remember, this is straight from your textbook. I mean, the same methodology. Of course, I just solved this. This is an example I just wrote. But the solution technique is the same. First, I look at the cost. Remember, we minimize the cost given a value-added target, right? So in this problem you see here, which is in the same form for both firms, value added is a given target. So firm wants to determine how much labor it needs to produce a particular value added, okay? And of course, then the solution has to respect this constraint, right? And then LG is equal to VAG divided by theta G, and LD must be equal to VAD divided by theta D, right? Because this is a constraint. So given that constraint, VAG, given that value added target, and given productivity, this is what the green firm needs in terms of labor, and this is what the dirty firm needs, okay? So this is then very simple, right? We can write total cost now. I mean, when I say total, this is total factor cost. So WLG now is written as a function of the factor price, right? It's a function of the factor price, and it's a function of the value added target. Similarly, for the dirty firm, exactly as in your textbook, again, this is the same technique. We have the factor price and the value added. Okay, and since this production function here is constant returns to scale, right? This is linear, so it is constant returns to scale. So it satisfies this particular assumption. Then we see that the price of value added is separable. So the cost is separable into price of value added and the value added, right? Remember, price of value added is the cost of producing 1 unit of value added, right? So here we can then find these prices, price of value added for green goods and the price of value added for the dirty good. Okay? Because again, constant return to scale assumption allows me to write the factor cost in these ways. Okay? Now there is also intermediate input cost, right? Because the green firm is going to use some of its own output and some output or some output of firm D, and the dirty firm will use some of its own output and some fraction of output from the green firm, right? So if we write these terms, then we find these cost components. So this is the intermediate input cost. Okay, this is for firm G, and this is for firm D. How do I know that? Well, this depends on the total output in G, right? Again, this isn't a very simple model. And of course, we assume that the price of the green good is equal to 1. So these parts are equal to 1. And here we have the price of the dirty good. All right. So the total cost now can be written, right? This is the total cost of the green firm, this one. So it depends on the factor cost, the cost paid for labor, and the cost paid for intermediate inputs. Okay, so we can write it in this way by basically summing this and this, and then we do the same for the second firm, the dirty firm. And of course, value added is also replaced, right? Because value added is equal to VI times YI, right? So we also replace that, and we expressed here the total cost as a linear function of output. Do you see? You see YG here, YG here, YG here, and YD here, YD here, YD here. This is again constant returns to scale assumption, right? The production function is linear, so at the end I can write total cost in this way. Now, if that's total cost, the average cost is simply this. Now, this is before tax. All right, so this is the average cost before the firm paid the tax. Okay, because this firm is going to face these costs anyhow, right? Regardless of whether there is government, whether there is taxation. Okay, but now profit will be written in this way, right? So this is now after tax cost. Okay, because the taxation increases the costs, the total costs paid by the firm. All right, so for the green firm, we have the total revenue, right? Total revenue is price times output. So price is equal to 1 by normalization. So output is YG. And the total cost faced by the firm is written in this way. Okay. And we have the profit of the dirty firm. Similarly, there's the cost, tau d, and then we write it in this way. Now we have all the components, and now we can look at the equilibrium. All right. Now first, we're going to look at the market clearing condition for the dirty good. Remember that the market clearing condition for the green good is assumed away, right? Because this is going to clear. This market is going to be cleared by the Walras law, right? So if I write this supply and demand condition, I have this, right? So this is supply for the dirty good, and this is total demand. So total demand has two components. One is consumption demand, which is there, right? And the other is intermediate input demand. Okay, intermediate input demand is originating from the green firm and the dirty firm itself. Okay. Now I want to write the market clearing condition for labor. This is the general look, right? Labor supply is equal to the sum of labor demand levels by two firms. Then I replace them with their solution. So value added G and value added D, of course, must appear in this way because these are the solutions of labor demand by the firms. Then I also eliminate value added from the model, and I write labor market clearing condition in terms of output levels. Okay, that's also key. So here, as you realize, I am reducing, I'm making the dimension reduction using algebra, not in matrix notation, right? Because this is a small model, and I don't really have to use the matrices. Okay. Now, what else we have? Of course, we have profit, zero profit conditions, right? Zero profit conditions. Now, remember that these zero profit conditions are expressed in this way. So price of value added will be written. So this is price of value added, right? The terms in the brackets. But then there is the tax. So the price must be before tax average cost times this 1 plus tau. Okay, the same is true for the dirty firm. Again, exactly as in the textbook, the same technique, but the model is now much simpler and we are writing everything explicitly. Okay. Now at the very end, of course, you know that the government budget constraint must be satisfied, right? Because government collects taxes from the firms. This is the revenue, and revenue is an endogenous variable. And then the government gives this revenue to the household as a lump sum transfer, which is T, right? So there is no other role. There's no other spending. There's no other source of borrowing, or there's no other source of revenue. So we want to write the total tax revenue of the government, and it is that. Right? Why? Because this is the average cost before tax. This is total cost before tax. And that's the part paid to the government, right? A fraction dependent on tau G by the green firm is paid to the government, and the fraction tau D by the dirty firm is paid to the government. Okay? And this total revenue must be equal to T. So the transfer, total transfer the household receives must be equal to that. Okay. Now then, we have 5 equations in 5 unknowns. So exactly as we require, our system is square, right? 5 unknowns and 5 equations. What are these 5 unknowns? W, PD, YG, and YD, and T. Okay, so output levels, lump sum transfer, one factor price W, and one output price, PD. Okay, and these are these equations. Okay, so look at them. What do I know here? I must know alpha. I must know these A coefficients. I must know V coefficients. I must know theta coefficients, right? These, if these coefficients are known, so this, as you realize, is a nonlinear system, right? Because here you see nonlinearity, right? So for instance, so right here, you have the nonlinearity. Okay, right here with YD multiplied by W, you have nonlinearity. So how I did solve this model? I did it over MATLAB. All right, now let me show you how I did it. So if I open my I share my screen, do you see now a code? All right, okay. Now this is called MATLAB. So this is a software by MathWorks company, a US-based company, and this is a software for computation. It's an advanced software. It has many different toolboxes, many different researchers. I mean, researchers from many different fields, scientists, economists, sociologists. Many people are using this. Okay. So why am I doing this here with MATLAB? Because I'm really fast at MATLAB, okay, compared to GAMS. So I wanted to do it in MATLAB for time efficiency. All right. Now here, this is the script I wrote for this example, dirty green text. So it is dgtext.m. M is the file extension here. So these are some clearing commands. So CLC clears the command window, clear command clears the workspace, and close all basically closes all the windows and other stuff. Now here are the parameters, right? A GG, a GD, a DG, a DD. So I directly assign these values, all right? Then I have VG and VD. I also directly assign two values to them. Then these are the tax rates, tau G and tau D. And I also have thetas, all right, theta G and theta D. Remember, these are production parameters, productivity parameters. I have alpha in the utility function. Alpha is for the green good, all right? So alpha is the budget share of the green good. And gamma will be the externality parameter that we haven't seen yet, all right? Now, these parameters are here, okay? The same ones. And in each experiment, I will show you different taxation schemes, all right? For instance, we're gonna start with no taxation, all right? But these parameters will remain same, all right? AGG, AGD, ADG, ADD, VG, VD, theta G, theta D, and alpha will remain the same, okay? Until I think at the very end, I will play with the productive parameters as well. But in general, sorry, they remain the same. Now, the first example is that there is no taxation. Now, I go to my code, okay? I go to my code and set the tax rates to 0, right? I set the tax rates to 0 and save it here. Now, here there's an if condition, okay? Why do I need this if condition? Because if both taxes are 0, this equation drops from the system, right? If both taxes are 0, the last equation, equation 5, is not part of this system. T is always 0, right? So I have to discriminate these two cases. For this reason, I write this if condition. So if both taxes are 0, then T is 0, then my system has 4 equations and 4 unknowns, All right. As you see, I write them as I see it in the paper, right? These 4 equations, I write them exactly as I see them because I am using the symbolic math. Okay, so when I define these symbols, PD, W, YG, and YD, MATLAB realizes that they are now not anything, but they are basically symbols. So I write these symbolic equations, all right? So there's no difference between writing them in this way or in this way in the paper, okay? The only difference is that I write them by equating it to 0. Okay, for instance, YD minus the demand components, right? 1 minus the labor demand by the green firm minus the labor demand by the dirty firm. Price is equal to gross tax rate times the price of value, 1 minus, right? PD is going to be equal to that, but I write it in this way, minus. Then I basically tell MATLAB to solve the model, right? First, I write equations. So this is a particular command that MATLAB understands, okay? And these are the unknowns. Then I evaluate my solution, okay? So solution is S, right? The first is W, the second is PD. The third is YG, the fourth is YD. Now this is now, so these are now numbers because I evaluated them. So up to this point, they were symbols, okay? Here, I define them as symbols. Here they are symbols. Here they are symbols, okay? But at this point, W is a number. Why? Because there is a solution there. PD is a number, YG is a number, YD is a number. Then I calculate the rest of the model. Okay? I calculate value added, I calculate LG, I calculate consumption levels, I calculate utility. All right? Don't forget about that. I mean, forget about this. This will be externality part, the second part. Now, I also know PG, right? PG is equal to 1. Then I have all the variables and I can create tables, all right? Now let me run the model. Oh, sorry. I also have the else part, right? What is else? So remember the if condition. In the if condition, I have both taxes equal to 0. Okay? So if one of these are not 0 or none of these are 0, is 0, then this part will execute. Okay, the MATLAB will look at directly to this part. Then we have 5 equations and 5 unknowns. All right, and the logic is the same. Okay, now T is also a symbol here, an unknown, and there is this 5th equation written as a symbolic equation, and then I have the code. Okay. Then I have the evaluation again. So after this point, these are just numbers. So I can calculate everything. Now here, of course, there is consumption demand in the tax, etc. All right. So when I run this, results will appear. Okay. Forget about the last part. Now, these are the results, okay? So these are parameters of this specification. Remember, both taxes are 0, so the found value of T is equal to 0, okay? Labor demands are there, consumption demands are there, output levels are there. So we have this. Okay, no taxation. So what is going on here? Look at the price levels, PG and PD. PG is normalized to 1, right? And PD is now around 0.6. So the price of the dirty good is less than the price of the green good, all right? And the alpha is also lower for, so the utility share is also lower for. So consumers relatively prefer more, their preference is relatively stronger for the dirty good. And also the technology is more productive for the dirty good, okay? And without taxation, there is of course this large difference between output levels. So the economy produces around 27 units of dirty output and around 12 units of green output, okay? And the utility is equal to 2.7. This is under laissez-faire, okay? Now, if I put the tax rates, equal tax rates, 0.1, okay? I got these results. Now, what does change here? Well, when I tax the goods with an equal tax rate, that's important. The tax rate is equal and everything is the same. Every other single thing basically as before. Now I see an increase in the price of the dirty good, okay? And a slight decrease in the output of the dirty good and a slight increase in the output of the green good, okay? If you look at it, there is a very small decrease in the output of the dirty good. There's a very small increase in the output of the green good, and there's a slightly more sizable increase in the price of the dirty good. All right, consumption levels change accordingly, and also there is a very small decrease in utility. All right, why? Let's think about it. Why do you think utility decreases, although the decrease is very small? Well, utility decreases because in this model, there is no externality, no public good, no asymmetric information, no missing market, okay? So there is no need for the government involvement, all right? If government puts these, if government implements this taxation, it basically distorts the market, okay? So in terms of Pareto rankings, this is now a worse equilibrium for the household, all right? Because market efficiency is distorted by the government with no reason, right? There's no externality here. So even if there is dirty good, household does not get this utility from this in this version, okay? So that's important. Now, if you play with it, now what do we see? Now, we tax, in this example, only the dirty sector, and we are not gonna tax the green sector, okay? And we're gonna put a huge tax rate on the dirty firm, okay? This is a huge 70%, all right? So I really want to decrease the dirty output, okay? I really want to decrease the dirty output, and I heavily tax the dirty sector, the dirty firm, and now what I see is that now the price of the dirty good is larger than the price of the green good, okay? Now there is a more sizable decrease in the output, but still the dirty output level is greater than the green output level, okay? What happens to utility? Well, now I distort the market even more, so utility is even lower, All right, because again, there is still no externality in the model. I haven't put it in there yet. Okay. So we're going to continue with these examples and try to understand the mechanics of the model after the break. So, but let me stop here for a very quick questions of yours. Otherwise, we're going to meet at 10:20. If you have a very quick question, I can answer it. But it's pretty simple. So once you get the logic of the model, it's quite intuitive actually. All right then. So let's take a break here and meet at 10:20. All right. Is that good for everybody?
Tamamdır hocam.
Okay. All right. I will see you at 10:20. Bye bye.